our next session in the Social Science Data Lab. We're very pleased to have Julian Schuessler here today from the University of Konstanz, who is going to give a 90-minute talk or workshop on causal graphs. Those of you who are here in attendance today see Julian in person. Those of you who are joining us via live stream now see this picture of Julian. Julian, as I said, is a PhD candidate at the University of Konstanz, where he started in 2016. He's recently joined the Cluster of Excellence on the Politics of Inequality and the Horizon 2020 project EU3D at the University of Konstanz. And importantly, he has recently been awarded the 2019 Causality in Statistics Education Award of the American Statistical Association for his undergraduate teaching materials on causal graphs, which are freely available on his website. Julian's research focuses on political economy, substantively the public support for the European Union, and his methodological expertise includes non-parametric causal inference and Bayesian statistics. The usual disclaimer for everybody here in this room today: as you know, we are streaming and recording this session using screen share and audio recording, which means that your questions and comments will be recorded. If you are not happy with that, feel free to join the live stream anonymously and post your questions in the chat there, or just write them down on a piece of paper and hand them to us, and we'll read them out for you. All right, that being said, we're switching over to Julian's slides. The floor is yours. We're very happy to have you here today.
Yeah, thank you so much. So thank you, Dennis, for inviting me. Such a great turnout. I'm very excited. It's my first time in Mannheim. It's my first time at the University of Mannheim. It's my first time that I do such a thing like this kind of format. I think I have a lot of material. I think I have a lot of exercises for you. So if you don't have a pen or paper yet, pick one up here. Some of it might be quite demanding. So if you think it's crazy hard or you don't understand anything, it's totally my fault and not your fault. You can interrupt me at any time. And for the one person live streaming this, hello as well, I guess. Okay, so I would like to start with asking whether you should be interested in causal graphs. So you can ask experts on that, and some will say yes and some will say no. One person who says that you should not be interested in causal graphs is Donald Rubin, who might be the most important statistician alive, used to be at Harvard. He says that the insights offered by the graphical approach to causal inference are generally not helpful. Okay, so now is your time to leave if you agree with Donald Rubin. On the other hand, there's people like James Robbins, who might be the most important biostatistician, who's also at Harvard. And he once said that there are a lot of people who never use graphs, who are well known in causal inference, who use this to the extent that they say we shouldn't use graphs. The famous saying in science is, science progresses on the deaths of the older scientists. And I don't think graphs will have any trouble in the future. Okay, so James Robbins says you should learn graphs. Then there's also Guido Imbens, the leading econometrician in the world, who's recently wrote a paper on causal graphs. And he says that the DAG approach fully deserves the attention of all research and users of causal inference as one of its leading methodologies. And finally, if you look for jobs outside of academia, you might encounter ads by a company called Facebook. Occasionally, such ads say knowledge of causal graphical models is a plus. Okay, so one more reason to look into it. Speaking of the DAG approach, oh no, not speaking of the DAG approach. Let's start with some quick questions for you so that I get an impression of what you know or don't know. Okay, so I have a series of questions for you just to start off. So just by show of hands, how would you rate your knowledge in so-called potential outcomes counterfactuals from very good to nada? So who thinks he has a very good knowledge? Good knowledge. Oh, nice. Okay. Okay knowledge. A bit and nothing. Okay. Okay. Well, this looks good. And the same question, how would you rate your knowledge in causal graphs? So who's an expert? I'm an expert. Who has a good knowledge? Who would say he has an okay knowledge? A few people. A bit of knowledge, a few more people, and no exposure. Okay, that's good. Then at least some people will learn a bit, I guess. Okay, then here's a question which is really just for myself because I'm always curious about this. It's a very specific, and you might think it's a peculiar question. You see this equation, and you've seen it before. Y equals x beta plus epsilon. The question is, when does beta stand for the causal effect of x on y? Again, just show of hands. It never does. Who thinks it just never does? Okay, no one. Who thinks it always does if a researcher says so without further assumptions? So who would say that? No opinion. Okay. Who would say it does if the conditional mean of the error term given x is 0? Also no opinion. Okay, that's okay. I know it's a very peculiar question. Maybe we'll return to it, maybe not. Let's start off with what I think is probably the most common situation for you guys if you analyze any kind of data. You're interested in the effect of x on y. There's another variable z. You think about whether you should control for it in your statistical model or somehow a matching or whatever. Now, you could think of a rule that tells you whether you should do that. And such a rule should have two properties. The first one is the rule should tell you which variables you must control for. And the rule should tell you or should never tell you to control for something for which you should not actually control, because it produces problems, okay? So that's two simple requirements we could ask for when we think about such a rule. And now I'm just interested in what you guys think are appropriate rules, okay? So again, we're interested in the effect of x on y. We have other variables z, and let's say, or who thinks it's a good idea or who thinks it's okay to control for z if z is associated with the outcome. Okay, a few people, okay. You should control for z if it's associated with the independent variable. Okay, a few people, okay. You should control for if z is unaffected by x and associated with both x and y. That's the Koske-Imai textbook criterion. Okay, people are nodding, more hands. Okay, I think that was actually in your presentation on potential outcomes. You should control for z if it affects y. Sounds good to 1, 2 persons, 3 persons. Okay. You should control for z if conditional on z, x and y are independent. Anyone thinking that's a good rule? 2 people. Okay, and finally, you should control for z if conditional on z, x is independent from the potential outcome of y when x is set to a small x. Anyone think that's a good rule? I think that's a good rule. In fact, it's the only good rule because all the other rules violate the 2 requirements. So they will fail in telling you which variable to control for, or they will tell you to control for something for which you actually should not control for. The only rule that is valid in general is this one, but that's not really a rule because it's really hard to understand, okay? And this rule, this would be a potential outcome of y. And this is the essential assumption in the potential outcomes framework of causality. It's sometimes called conditional ignorability. And again, in English, it says that conditional on z, the potential outcome of y when large x is set to small x is independent of x. I personally think this assumption is hard to understand. And hopefully we'll get to a point where you understand this assumption better using causal graphs. Okay, that's one of the aims for today. In fact, I will talk about DAGs, that's directed acyclic graphs, but I will actually talk about it from the perspective of what's called structural causal models. That's the work by Julian. And in short, that means that graphs are understood as structural equations which define potential outcomes. I'm not going to explain that in detail. But the important thing is that this potential outcome thing and the DAG thing are fully compatible. And actually in that framework, you need both. Like you definitely need potential outcomes for a few things. There's just no way around it. And DAGs are just tremendously helpful in understanding what's going on. And crucially, every assumption you can think of that you can write down using these potential outcomes, you can draw a graph for that implies these assumptions. So this is one of the reasons why graphs are so tremendously useful. If you follow Twitter, there's a huge discussion between economists and Julian and other people on all of this. And I think like this point just gets lost because from a mathematical point of view, there is no formal difference between graphs and potential outcomes. In a certain sense, they're equivalent. The question only is like what's the best representation that we work with as empirical scientists? And how easy is it to understand this representation? And naturally, I would say that graphs are really easy to understand. Questions so far? Are there any more people online?
Yes.
Cool. 4. Nice. Okay. So what I'll cover in the next, I don't know, 45 minutes perhaps, or an hour, is 3 main problems and 3 main tools that you encounter when you think about this stuff. The first one is fundamental and entails understanding what a certain graph implies in terms of correlations between variables or the absence of such correlations. That's the first problem. Second problem is to think about what a causal effect actually is. It's like, how is it defined and how we would identify it given certain assumptions. And the third one is, and this I'll just touch upon shortly, is how to think about potential outcomes in this framework formally. Okay, so let's start with a DAG. So again, DAG stands for directed acyclic graph. It's directed because the arrows have little tail heads. It's acyclic because there's no circle in it anywhere. It's recursive. We have 3 variables, d, m, y. We have funny epsilons. These are dashed. That I use that to indicate that they're unobserved. These variables here are observed. And my question to you is just intuitively, or just from the top of your head, which assumptions are depicted in this picture? So does anyone see any kind of assumption that we depict here? Yes?
D affects y only through F.
Yep, that's a good one. So that hopefully should be clear. We don't have an arrow that goes like this. Yeah, perfect. There was another show of hands. Yeah.
So there are arrow terms. So it means that there's a measurement arrow.
Ah, okay. Could you expand on that? So for example, what's a measure of what?
D, M, and Y are affected by different variables that are not depicted or that are not D and M.
Uh-huh. Okay. Yeah, I think so you could say that, for example, D is a version of these variables that's I actually couldn't say that. So but it's an interesting point. Okay. But what kind of assumption is entailed there?
We don't know.
You don't know what?
We don't know the arrow.
Yeah, okay, it's unobserved. Yeah, that's crucial and important. Yeah, in the back. Yes.
Yeah, but in addition, we assume that the respective unobserved factors only affect the corresponding element, and for example, epsilon t doesn't affect any.
Yep, that is also very important. So there are arrows missing from here to here, from here to here, etc., etc., etc. Any other ideas? Like Dennis, anything to add?
I think most of what I had in my discussion.
Yeah, I think you got the most important elements. Oh yeah.
Yeah, may I ask in this graph, for example, if n exists alone, would it equals 1? That means if d doesn't exist at all, and so long as n exists, equals 1.
So, could you say that again? So,
for example, a variable n exists, will it directly into y as such without d exists?
yeah. So you mean if that would be left out, then we would just have a simpler graph with m affecting y. Does that answer the question?
Yeah.
Okay. Any other question? Okay, cool. So the important thing is that the assumptions are the arrows which are not there. So there's no arrow from d to y. There's no arrow from the errors, for example, from epsilon d to m and y, etc., etc. Also, there's no reverse causality. There's no arrow from m to d or from y to d, etc. And this is fundamental and very important to keep in mind. The assumptions are the arrows that are not there. From a psychological point of view, that's not perfect, I guess, but that's just, I mean, that's just how it is. The important assumptions are the arrows that are not there. If we draw an arrow, we're just saying it could be there, okay? Doesn't have to be, but we just allow for the possibility. Any questions? Cool. So here's a first exercise that you can solve on your own or with your neighbor if you want to. I want you to draw what you think is the instrumental variables graph. So perhaps a few of you have a graph in mind. If not, just look at what your neighbor is drawing, where Z is the instrument, X is the treatment, Y is the outcome, and you have unobserved confounders U. So just take 2 minutes, just, you know, there's no right or wrong, just what you think about instrumental variables. The easiest case you can imagine.
We'll mute the live stream in the meantime. If you guys online have any questions, please post them in the chat, and we'll be back in 2 minutes.
So I'm going to ask the nasty questions. So is anyone willing to share his or her graph and draw it for me and the audience? Okay, that's not the case. That's okay. So here's what I think the prototypical graph looks like. So again, Z is thought of as the instrumental variable. This should be an X. Here it's a D, whatever. This is the treatment. This is the outcome, and the U are the unobserved confounders. And for example, there's no direct effect of the instrument on the outcome, the exclusion restriction, etc. And the problem is unobserved confounders influencing both the treatment and the outcome. Any questions, any comments? Anyone disagreeing? Okay, okay, cool. So that's the prototypical instrumental variable graph. Historically, instrumental variables were developed using causal graphs in the 1920s. So that was Schuessler, a biologist who later received the Nobel Prize in biology. He had a brother, Philip Wright, who was an economist. Schuessler was the first one to use causal graphs. Philip Wright was the first one to develop instrumental variables. And there's a tight connection between the two things, both biographically and substantively. But now I have a specific question. which is, suppose this is the case, and we measure z, d, and y. We do not measure the u. That's our problem. And now we're running, for some reason, we're running a regression of the outcome on the treatment and the instrument, which might or might not be a good idea. The only question is, will the coefficient on z be 0? And just quickly discuss with your neighbor whether you think yes or no and why it's the case or why not. Just think about it. Just talk to your neighbor. I think you need more time. Okay. Impression is that this is somewhat controversial. So who thinks this is a tricky question? I think it's a tricky question. Okay, roughly half of the people would say it's a tricky question. Who thinks the coefficient is 0? 1, 2, 3, 4, 5, 6, 7, 8 people. Who think it's not 0? 1, 2, 3. Okay, so a relative majority thinks it's 0. Would it be nice if it were 0? Would that be helpful? Why would that be helpful? I saw you nodding.
Then it's perfect instrument.
Okay, so yeah, so it would be like a test, I guess, right? Whether the instrument is actually an instrument. Okay, but you know there's no such thing. Okay, so yeah, so the question is, we want to know whether a certain graph implies independencies between variables. Okay, I was asking you whether conditional on D, Z and Y are independent. If they were independent, the regression coefficient would be 0, right? The question is whether conditional on D, controlling for D, whether Z and Y become uncorrelated. And that's the first question we're going to answer now. And the concept we need is called D-separation. Okay, so let's talk about D-separation. It's super straightforward. So this is a very simple graph. You've seen it before. D influences M, M influences Y. Will you have a question?
Oh, no, sir.
Okay. Will D and Y correlate in general? Yes or no? Yes. So D influences M and M influences Y. If both things are positive, for example, we would expect probably to have a positive correlation between D and Y. You know, in general, this could be any kind of treatment. This is a mediator. And that's just like the process of how D produces changes in Y, okay? So we agree there should be a correlation between D and Y. What happens when I control for a condition on M? So I'll look at a subset of the data where M is constant. I'll look at the correlation between D and Y. Should there be a correlation? Any ideas? People are shaking their head. Yeah, I hope that's intuitive, that if I control for M, I block the information flow. So you can literally visualize it as information or water or fluid like moving from the left to the right. If you block the middle thing, you stop the information flow. So we would say that the path is open, conditional on M, it's blocked, which means that D and Y should correlate. If you control for M, they should not correlate. Okay, that was the first bit. Here's some code for you, or for the people live streaming this, how to simulate this. Because it's super easy. You just translate the graph into some R code. D is just any kind of a random variable here with 1,000 observations. Then M is a function of D plus some noise. Y is a function of M. I forgot the plus some noise. When you look at the regression of Y on D, it's going to be like minus 0.24. That's going to be the regression coefficient. And here the coefficient on B is going to be 0. You can do this at home. Okay, here I switched this arrow. So now M influences D and Y. So you could say that M is a confounder. Same question, do D and Y correlate? Yes, that's like omitted variable bias. You have a third variable that influences D and Y. So for that reason alone, D and Y correlate. Think of the season, ice cream sales, people drowning. All right, when it's summer, people buy ice cream, people drown because they take a swim. If it's winter, it doesn't happen. So ice cream sales and whether people drown correlates, I guess. Same question, what happens when I control for M? In this graph, do D and Y still correlate? Some people are shaking their head. The answer is no. Kind of similar reasoning. If I condition on this thing, it blocks the connection between the two variables. There's no effect of D on Y, so there should be no correlation if M is the only cause of these two variables. So again, this path is open, D and Y correlate. Conditional on M is blocked. D and Y do not correlate. Okay, so that was 2/3 of what we need to know. Here's the final bit where I switched both arrows so that the arrows collide in the middle variable. Same question, what do you think? Do D and Y correlate? Who thinks no? Who thinks yes? Okay, so why do you think they correlate?
Because the in pure correlation, the direction of the association shouldn't matter. Like just model it with R, just direct. Like for pure correlation, it shouldn't matter.
Okay. So one example, I'll show you another in a second. One example that I use for understanding this is a random coin flip. This is a random coin flip independently. So this is 0, 1. This is 0, 1. It's two binary variables. This is the sum of the two things. So if both are 0, this is 0. If just one has a 1, this is 1. If both are 1, the sum is 1. So clearly, random coin flips do not correlate. You cannot predict the one with the other. When I tell you the result is 1, this is 0, you can perfectly predict that this has to be 1. So conditional on the thing in the middle, these two variables are correlated. So D and Y do not correlate, perfectly independent processes. However, once I control for the middle thing, or once I know the middle thing, they do correlate, because when I know the process of two independent inputs, I know the result, I know one of the inputs, then I can say something about the other input. So the path is, shit, that's wrong. So the path is blocked. Conditional on M, it is open. I'm sorry, this is a mistake. Okay, the path is blocked because D and Y are just completely independent things. No prediction possible. Once you control for M, there's going to be a correlation. Here's another, and we say in graph terms, M acts as a collider because the arrows collide in M. Here's another example about articles, about scientific articles, some of which might be newsworthy, some of which might be rigorous. Let's assume there's no correlation, no connection between these two features. Both things probably make it more likely that the article is published in Science, the journal. So that means that you read an article in Science and you realize it's not rigorous, then that's got to be because it's newsworthy. And when you read an article in Science and you see it's newsworthy, then you can predict it's probably less rigorous than average. And I think that's true. And that's also a collider phenomenon. Questions on the collider or on anything else? Okay, nice. So to sum up, we started with this chain of mediation thing going from left to right. We noted that the path is open. The first and the last variable correlate. Once you control for m, they become independent. You can write this down like this, where this funny sign just means independence, which implies a zero correlation. Then we had the confounding common cause fork situation, where m is like the confounder. Similar result, the two other variables correlate. Once we control for the common cause, they become uncorrelated. Yes, please.
I have a question on the preceding slide.
Yeah.
I mean, isn't this just the natural case where you have different predictors for an outcome? For example, success of something is predicted by income and education.
Yeah.
Why can you then say, okay, so he's high on education, so probably he's low on income? It seems to be the implication of what you said.
So you're saying you're predicting something with education and income. So what are you predicting?
Or education and family background, and you predict later income, right?
Yeah.
For example.
Yeah.
And
so that would be the outcome in the middle. But the regression you would run is that would be the regression outcome, right? So here I was saying, suppose I know an article is published in Science, and I also know it's newsworthy. Can I then predict whether it's rigorous? The answer is yes. So the regression equivalent would be, that would be the outcome, and these two things would be the explanatory variables. So in your example, you would predict family background by income and education. Even though in the story, income is the thing that is the effect, the cause, right? Okay. Okay. Okay, chain of mediation, common cause. And here's another typo. So this should be collider. In the collider case, the path is blocked because the first variable and the other variable are just completely independent. But once you condition on the middle node, the two things become correlated. And in directed acyclic graphs, there's no more scenarios. You can build any more complicated graphs just by stacking these things together. There's just no other scenario that can occur. So that means we've now understood how graphs imply certain correlations or independencies. And specifically, we can also say something about situations where the path between two variables is much longer, because we just look at whether any of these elements are in that path. We check whether we control for something, and then we can say the path is blocked or the path is open. And so deseparation says, first of all, we look at the paths, and we say the path is blocked by a set of variables z if the path contains this mediation chain or the confounding chain, and we do control for the thing in the middle, then the two variables become uncorrelated or the path is blocked. Or the path contains a collider and we do not control for the middle thing, then the path is also blocked. And then we say, if some variables block all the paths between two variables, then we say x and y are deseparated conditional on z. And then that means that they are independent and uncorrelated conditional on z. So that's a mouthful, I know. But the logic is there's three different prototypical paths. Each longer path will contain one or two of these things. And then if you run a regression, you control for other variables. If these variables block the path and all the paths, then a certain regression coefficient will be 0. We also say that if this is the case, then the graph has a testable implication. because if the graph says certain variables should be uncorrelated, conditional on other variables, that's something you can check, provided that you measure those variables. And D separation, the D stands for directional because we're talking about directed graphs. So let's get back to the instrumental variables graph. I asked you, for some reason, you're running a regression where Y is the outcome and Z and D are the explanatory variables. The question is, will the coefficient on Z be 0? And to predict whether this is the case, you have to write down all the paths between Z and Y, because that's the statistical relationship we're interested in. And then you check whether there are any open paths when you control for D, because the regression controls for D. So just take a sheet of paper, take 3 or 4 minutes, try to enumerate all the paths that between Z and Y that you see in the picture, and then you can talk to your neighbor if you want. Any questions on this? Anything not clear? So I think this is demanding, so just let's just see how it works, and we'll talk about the solution in a few minutes. This slowly. I'm gonna like this. Yes. So can anyone let's enumerate all the paths between Z and Y. Can anyone describe to me what 1 or 2 or 3 of these paths look like? Any ideas? Yeah.
So there's Z going to X, going to Y, or D.
Yeah.
And then there's Z going to X, coming from U.
Yep.
Going to Y.
Yep. Any other path? No. So it's only 2 of them. And that's already interesting enough. Any comments on the paths? Anyone want to say whether any of these are open or blocked? So the first one you should recognize. The first one is just this chain of mediation, starting in Z, going through D to Y. So in this path, D acts as a mediator. So that means that if we look just at Z and Y, this is the reason why Z and Y are correlated. Z affects D, D affects Y, so Z and Y are correlated. In IV lingo, that's the reduced form, the regression of the outcome on the instrument. That's this one. If we control for D, we block the path because it's this chain of mediation thing. So if it was only for this path, conditional on D, Z and Y would be uncorrelated. Because there's just one connection, we can block it. However, there's a second path, and D is also in it. And if we control for it, we see that in this path, D has a different role. It's a collider. And so the path is blocked unconditionally, but once we control for D, we create a correlation between Z and U, and because U affects Y, we also create a correlation between Z and Y. So to summarize, this is blocked conditional on D. This one here is open conditional on D. So this together implies that Y is not independent from Z conditional on D. So a few comments. The fact that this path is blocked if you don't control for D is a good thing, because this is your instrument. These are the things that you cannot measure that produce the problem, and you don't want to have a correlation between these two things. Because the whole idea behind instrumental variables is that the instrument is uncorrelated with the confounders that produce your problem in the first place. Second, we just learned that even if the instrument is valid, which is the case, the instrument affects the independent variable. There's no direct effect. There's nothing else going on. It's the perfect instrument. Even though that is the case, there will be a correlation between the instrument and the outcome once you control for the treatment, which tells you that you cannot test whether the instrument is valid, because of course, if the instrument is invalid, for example, if you have a direct effect, then just because of the direct effect, you will have a correlation between Z and Y no matter what. Okay? So that means using regressions, you cannot test whether your instrument is valid. And we have proved this using deseparation as a concept. So to summarize, these are the two paths. The first path is mediation. It's block conditional on D. Second path, D is a collider. So the path is open conditional on D. So this implies in a regression of Y on Z and D, the coefficient of Z will be non-zero. Yes.
One question, I'm not really sure if it's a good question, but are the arrows associated? When you started asking those questions, I started wondering if you can put brackets around them, maybe twist them around or anything, but I'm not because those aren't like, those are this is the direction of the influence, right? This isn't the same as a logical implication. So would you be able to put brackets around, say, is Z implies D implies Y the same as bracket open, Z implies D, bracket close implies Y?
Say that again. So this is the same as what?
As brackets around Z and D.
Brackets around Z and D, like this. Oops. Okay. Yeah, full screen snap. So like this.
Exactly.
And what would that, like, what's that supposed to mean, the brackets? I don't quite understand.
Well, that only, yeah, you're right, it wouldn't make any sense. It's only,
Perhaps in the second
Path.
path, let's say if you have brackets between D and Y, so
D and Y, like this.
Yeah.
But again,
and it just like perhaps a better.
yes, this won't make any sense.
well, maybe, perhaps I just don't quite get what the brackets would like actually mean, but perhaps we can talk about this later and clarify. Okay. Any other question or comment? Yeah.
This in the graph we draw, there's a direct arrow from Z to y.
Yes.
But here, no.
Yeah.
My question is, how can you ascertain whether there is direct effect from z to y, but
Yeah.
not from the confounding factor?
Yeah. So this, of course, is a substantive or theoretical argument you have to make. If we're talking about an encouragement design, like a field experiment, where this is a randomized phone call to people. If they pick up the phone, they get a certain message on getting to turn out the vote, and then you measure whether they turn out in an election. And then you can randomize whom to call. And for that reason alone, the U cannot affect the Z, because Z is randomized. That's also a very fundamental point, and we'll return to this. Okay, so that would be one kind of line of reasoning to justify this graph. And also the fact whether your phone rings can only affect whether you vote if you actually hear the message. Because otherwise, just someone called you, and it's plausible to say that this fact alone does not directly affect whether you vote. Okay, so that would be one kind of justification. Any other question? So the good news is with like deseparation that's most of all what you need to know. I mean, if you grasp like how deseparation works, that's really 80% of the work that you can do with graphs. So that means we've covered quite a bit now. And as usual, it's a question of practice. So you just have to do it 10 or 15 times with different graphs. I'll have another one later for you, okay? And yeah, and now's the time actually. So here's just a second exercise, which is slightly more complicated. So again, it's totally cool if you don't fully get through it. This could be read as a mediation model. So D is the treatment. There's two mediators, W and M. There's your outcome Y. There's the direct effect. There's an indirect effect. There's another indirect effect. The question is, does this graph have any testable implications? And you determine this by checking for every pair of variables E and M and in Y, whether they are ever deseparated somehow. This is somewhat cumbersome because there's 4 variables, so there's 6 pairs. Here's a hint. Variables that are directly connected can never be deseparated. So D affects M, you cannot erase this thing somehow. So these probably are going to be correlated no matter what. Okay, so take a sheet of paper, probably start doing it with your neighbor. That's faster, and try to determine whether you can test anything here. We should go on. Okay, so let's do this. So, is there any pair of variables that can be deseparated somehow? Yes?
W and M can be separated, so they should be independent, conditional on D, but unconditional of Y. Because Y should stay blocked the way it is, and D should be blocked by control.
This sounds very, very good. Yeah. Any other pairs of variables that can be separated? No. Okay, so you got it. So let's check this. Actually, I'll return in the interest of time. Yeah, so it's about M and W. So let's look at the past between M and W. There is this one going from W to D to M, where D acts as a confounder. There's this one from W to Y to M, where Y acts as a collider. So this one is open, this one is blocked. there's this one, W, D, Y, N. Here again, D acts as a confounder, Y acts as a collider. So this one is blocked too because of the collider. And of course, if you could also start at N. It doesn't make a difference. Either or. Yeah, so we have 3 paths, I think. Any other paths? I sometimes forget them.
So you wouldn't write down the other combination then. So for the fourth one, for the third one, as you just said, so you can also go the other way around. That in interpretation, you just write down this.
Yeah, yeah. So you can start at W or start at M. It's the same path. Yeah. So this one can be blocked by conditioning on D. This one we don't do anything about it. It's blocked naturally. This one too is blocked by Y, and it's blocked twice if we also control for D, so to speak. So we conclude that W and M are D-separated conditional on D. How would you test this? Any ideas using data? So there's basically 2 ways. Either you run a regression where W is the outcome, and D and M are the independent variables, and the coefficient on M should be 0. Or you run a regression where M is the outcome, D and W are the independent variables, and W, the coefficient should be 0. Yeah. Any questions? Okay, so yeah, if you find that the coefficient is not 0, even though it should be, then there's exactly 3 possible reasons. Either you have misspecified the regression, that's just misspecification error. When you're doing hypothesis testing, it could be a small sample fluctuation and a type 1 error, or the graph is wrong, right? If there actually is a path from W to M, of course, they're going to be correlated. Yeah.
So with testable implications, you mean testing if our assumption is right, ergo if the paths we omit are really not there.
Yeah, yeah. Yeah. Yeah.
Is there an issue with, not sure if I can explain it correctly, with the connection between D and Y? So if we block D, doesn't it also like control for Y? Because
you mean if we control for D?
like in the third path, we control for D. Doesn't it like control for Y and thus open up the collider path?
That's a good question. No, the short answer is no. If we control only for D, we just control for D. We could, if the graph looked slightly different. So you run into problems if you have a Y star, which is a descendant of Y, a child in graphical terms. If you control for this, it's not a collider, but it's a child of a collider, and it has the same consequences. So this is the only case where we control for a thing and the father or mother is a collider, and that's the same thing. But if you control for D, D is not a collider on any path. It influences the collider, but that's not a problem. Okay? Yes?
So I would say in most of our work, we actually we measure something which is just a child of a latent variable that we're actually causally interested in.
Mm-hmm.
So don't we always have that? So I measure some attitude on a Likert scale, and I'm always interested in y star, but in y, but I'm measuring y star.
Yeah, so that's one of the reasons for why in the measurement error literature you see a lot of graphs, because these measurement error models can easily be depicted as a graph, and it makes perfect sense. Like, you know, D is unobserved, you observe D star, and perhaps it influences Y, but you only observe Y star. Under what assumption can you recover beta, etc.? Yeah, so obviously there's 10 million papers on that. No, so it's a problem and you have to deal with it. Any other question? So we have 20 minutes to go. So I want to talk about causality, because deseparation is just, we make some assumptions, they come from somewhere, from theoretical reasoning or not, just make them up. And then sometimes we can infer something about the absence of correlations, right? So let's talk about causal effects. This is the prototypical confounding graph. D is the treatment, Y is the outcome, X is a confounder. And as with potential outcomes, in the literature on causal graphs and structural causal models, how we think about causal effects is by invoking the metaphor of hypothetical control. So we think about a possible world where, for some reason, we could influence the value of D, and we could interfere with the system, if only hypothetically. So the question for you is, how does the graph change if we do that? So how does the graph change if someone somehow could manage to force D to have a specific value for just everyone, for example? What would that change the graph? Any ideas? Yes?
There would have been a connection between X and D.
Yep, that's the answer. Perfect. Yeah. So if anyone sets a capital D to small d, then that is irrespective of the value of X. X ceases to have an influence on D. In graphical terms, in the graphical literature, the formalization of this idea is the do operator, which I like because, right, you do something, that's good. And what you do is you set the large D to some small d, and this is an actual number, like 3 or 7.5 or whatever. And this is the connection between graphs and potential outcomes, because the outcome under this hypothetical intervention is, or the mean of this outcome is also the mean of the potential outcome with respect to D. And then the observed variable becomes the potential outcome of the counterfactual variable. And this, and I'm just really scratching the surface here, this is how you connect graphs with potential outcomes. Any questions or comments? So this also implies that in order to learn about the causal effect, one way to do this is to implement the do thing in reality. If you can't do it, then this is the graph you're faced with. And intuitively, if you measure D and Y, you get an association. The association consists of the causal effect of D on Y, this one, plus the open path through the confounder. So clearly, if you want to estimate the causal effect of D on Y, and if you cannot do that in reality, the intervention, you have to find control variables such that the bad, spurious, non-causal paths between D and Y are blocked using the similar logic as in deseparation, while at the same time, the good causal paths remain open. Okay? And also, you don't want to open up new paths via colliders. This is formally unrelated to deseparation. So deseparation just takes the graph, and then is only concerned with associations or non-associations. And in this mediation graph, I told you that you can use W as the outcome, or you can use M as the outcome. It doesn't matter, right? You're just interested in correlations. Deseparation is for testing graphs, and for deseparation, you want to look at whether all the paths are blocked, and you don't care about what they mean, all the paths. But for identifying causal effects, we certainly want to have some paths open by design, so to speak. So that leads us to the backdoor criterion, which says that if you're interested in the relationship between D and Y, some variables X satisfy the backdoor criterion if no variable in X is a descendant of D, that is to say, is influenced by D, and the control variables block all the paths between D and Y that contain an arrow into D. This path here, this part you can ignore. Okay, so let's dissect this. We're talking about an ordered pair because D is the cause, Y is the effect. If you reverse the order, that's a different question you're asking. A path that starts with an arrow into D is called a backdoor path because it enters D through the back door from behind. Blocking backdoor paths makes sure we block all the bad paths. Not conditioning on descendants of D, that's the first part, makes sure we leave all the good paths open and also do not open up new bad paths. And this is a good rule in the sense of 1 hour earlier. This rule tells you which variables you need to control for, and it never tells you to control for something which actually is bad. And also, this rule in the framework of structural causal models implies that this conditional ignorability assumption holds conditional on X. Okay. Any questions? So we have just 10 minutes to go. Right, the simplest case is here. There's one vector path, DUY, right? I'll show it to you. In this case, you have one vector path, DUY. Here's the backdoor. U enters D through the backdoor from behind, arrow into D. And this is the one path you need to block, and then you need to control for U. And then you, for example, can run the regression of Y on D and U. And then Y will approximate the causal effect of D. So since we have only 10 minutes to go, I can talk a bit about post-treatment bias, which combines the vector criterion with the concept from deseparation. I can also talk a bit about causal mediation, or we can just open up the floor if anyone has any question on anything. So who has a question on anything? Okay. So who wants me to talk about post-treatment bias? 1, 2, 3, 4, 5. Who wants me to talk about causal mediation? Bye-bye. 1, 2, 3, 4. So post-treatment bias it is. So what's post-treatment bias? Any Can anyone characterize it? Yeah.
So I guess in the language of causal graphs, you're conditioning on the descendant of your treatment that also has an error going into the outcome.
Yeah, that's the one problem, but there's a second problem. So the one problem is that obviously, if you have this idealized example where there's no direct effect of the treatment on the outcome, then you have one path between the treatment and the outcome. M is a mediator. If you control for M, the path is blocked. So in the regression of Y on M and D, the coefficient on D is 0, even though D has a causal effect. So this means conditional on M, D, and Y are deseparated, even though D may have an effect on Y. So the coefficient on D is biased for the causal effect. And perhaps you know the paper by Montgomery and co-authors in AJPS that estimate that about 50% of political science experimental studies actually do this, which is a problem. And I think that's intuitive. You control away part of the effect you're actually interested in. Okay. So any comments or questions? Yes.
But if D has a direct effect on Y, then its coefficient won't be 0.
Right. Yeah. So of course, if you have this, then you will still get a non-zero coefficient, but it's a different coefficient if you control for M. Bye-bye. And of course, in this case, you could justify it as a mediation analysis, and what you get is some kind of direct effect. But if you're interested in the total causal effect, you must ignore M. Okay, so that's intuitive, but it gets worse. So can anyone see how it gets worse in this case? Yes?
I will not find an effect because M and Y are not directly related, only to an unobserved founder, so basically nothing is working.
Yeah, so by assumption, D does not have a causal effect on Y, right? But you have one path between D and Y, it's D and UY. M is a collider. If you control for M, you open up the path. You get a correlation. It looks like there's a causal effect, even though it's not true. And in experimental studies, so this could be randomized, and this could be attrition. So perhaps influenced by the treatment, some people leave the study. You don't measure the outcome for these people. So if you run a regression with the data you have, you are conditioning on attrition by design, because you only get to see the outcome for those who go through in the study. And then this problem might occur. So that would be a sample selection bias. Nice. Yeah, and of course, you can have both problems at the same time. So here, D could be randomized, M is a mediator. There is a causal effect, and if you do control for M, you get two problems. You block a causal path, which you do not want, if you're interested in the total causal effect, plus you open up a new non-causal path, which you also do not want. Any comments or questions? Nice. Okay, then I think I'll wrap up. This blah, 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 blah. So to summarize, I think that everyone interested in causal inference should learn about causal graphs. I think it's just incredibly useful. Ideally, you learn about structural causal models, which is something I have alluded to, right? The combination of graphs and structural equations and potential outcomes, which can all be connected, and you can translate everything from one language into the other. The best textbook on the market to learn this is one of the books by Pearl. So he has the causality book, which is hard to comprehend. He has the book of Y, which is this general audience thing. And actually the least known, but probably best book is called Causal Inference, a Primer, is with Nicholas Jewell and Mariah Glimmer. And it's just a really nice textbook. It's really short. It's just like 120 pages, fairly small. You can read it in one day if you want to. Cannot work through it in one day. It takes considerably longer, but it really picks up on many things that I touched upon. It's a great textbook. And of course, self-promotion. I have slides on my website, which may also be helpful. So I'll leave it at that. Of course, we can, if you have questions, I'm happy to answer them or to discuss things. Thank you so much for having me. I thought it was really fun. So I'm happy if I have convinced a few people about looking into the stuff. And yeah, have fun with the research. Dennis, thank you again for inviting me.
Thank you.
And see you around. And to everyone listening, you can hear me, I can hear you, but thanks for dropping by. Okay. So I guess if people want to leave, they can leave.